Hello, welcome to another Midnight Maths video. In this one, we're going to cover probably one of the most important topics in AP Calculus and in general in math if you're going to be um, taking more math classes after this, and that is the chain rule. So, what is this? Well, in short, it's like, oh yeah, you can differentiate composite functions. But in this video, I just want to take like one approach to like actually using this in practice and just sort of informally exploring this a little bit. Hopefully this way will help you in a different way that perhaps other resources on the internet could not. So we have here, let's just say, like, of course we got to start with whatever our example function is, right? So this is a function, and then we want to differentiate with respect to x, okay? So now what we do, right, as you may know, is we use the chain rule. But, the chain rule is often written where you have, like, f of g of x, and then you say, okay, well, if you want to differentiate, you just go f prime of g, and then multiply by g prime. But I don't know. To me, this is a perfectly valid way of writing it, but to me, Leibniz notation is just a lot more elegant. And if you don't know what that is, well, let's look at it. So what we do instead is we say if we have an f of g of x and you want to differentiate, you can say, yeah, okay, let's just write this again, just to reiterate that this is a totally valid way of writing it. But how I like to conceptualize it is to say like this. So what we're saying here is differentiate f with respect to g and then multiply by dg with respect to x. Now, of course, what I'm about to do here is strictly a mnemonic. Please don't use this as a justification for like an FRQ proof or your teacher or anything. But, just to verify that you've written the derivatives correctly, the dg's sort of like cancel out. And that's one of the sort of neat things about Leibniz notation. You can sort of cheat like that. But it's nowhere near an explanation. But just to make sure that you've written the rule correctly. Um, so you have this. And it's like, okay, well, I don't quite get how this might, relate to this. Because these two, upon first glance, might look like pretty unrelated-ish. So, okay, let's sort of break it down then. Well, we have the dg dx, so this part and this part are exactly the same. Like, they are, like, exactly the same thing. They are just written in different ways. So we know for sure that that's the same. But now, that means that now with this term is equal to this term. But, they don't quite look the same on first glance, right? Um, and so this is one of the things where we're gonna see. So, for example, like if you have 4x squared plus 7, you start with x, and then you go to 4x squared plus 7, and then you go to this. So now what we might say is like this part we might say is like an inner function, and then this part we might say is an outer function. And then, we would continue like as normal. But another way of thinking about it, which I find quite elegant, is you say that this, right, is equal to d all this over d this inner part times d 4x squared plus 7 over dx. So, I mean, this is basically like I feel like this is like the heart of the chain rule right here. We've written everything very explicitly in terms of x. So where you might see like a g into f, I've replaced with, an actual function of x, just to remove that abstraction here. And I mean, the mnemonic checks out. The strictly mnemonic thing where you check like, oh, have I done all of my derivatives, right? Yeah, it seems to check out. It goes deeper than that, right? So let's. This I think is a pretty straightforward term right here, because this is just kind of like, you can use the other rules that you have probably learned in calculus by now, like your power rule, your constant rule, blah blah blah. You get like 8x here, right? But this is the one that's interesting. So how do you differentiate that mess in terms of that mess? This looks more complicated. Well, what we do here is like we have to revisit kind of what differentiation maybe means a bit. So when you write dy dx, you're sort of implying right here, at least in the scope of this derivative, if you will, that like y is going to be the dependent variable that depends on x. Now, whether it actually does, that is a different story, right? Because you've got like implicit differentiation where you just sort of assume that y is a function of x, and then you continue as normal. But it doesn't have to be y or x. It could be dA dB, right? And as long as you have like b as a function of like if you have a equals 3b, for example, then yeah, dA dB is pretty straightforward to figure out. It's just 3. Now, it doesn't matter if b is a square root of 4x cubed plus 5x squared. No, it doesn't matter because we are only differentiating with respect to b, right? So as long as you have this relationship right here, where you have a in terms of b in this neat like explicit relationship, then you can still calculate the derivative. So sure, and then if you say like, and so you can apply this the same way over here, right? So it's like, okay, these are kind of weird functions that I put on top of each other, right? And why have I chosen to differentiate this one on top of this one? Well, the only reason was because like the only difference between this function, and this function is a square root, right? There's a square root. I mean, that's pretty much the annoying part of this whole operation, right? Because this whole half, um, that part is sort of standard. We could have dealt with that without the chain rule, but it was just this part, the square root part, that was a little bit more annoying. So what I did here is I just said, okay, we'll differentiate the square root part with respect to whatever's on the inside. So now we actually don't even need chain rule for this particular derivative. We can just say, for example, just like sort of the reverse of what we were doing here, if we just say that 4x squared plus 7 is some letter, let's call it a, and so now you can rewrite the whole thing in terms of a. So you're just left with d root a over dA. And at this point, this is a standard operation. This is probably the most important part, is that the whole point of the chain rule is so that you can break it down into all these individual derivatives that don't require the chain rule on their own. But you're putting them all together, and then you get the chain rule, you get the derivative of like the compound function. So here, I mean, if I just gave you this like problem out of context, like find d root a over dA, well, you might say that's like d by dA of root a, right? These are different ways to write the same thing. And so you get 1 over 2 root a, right? So that is a pretty straightforward operation. But now the problem is we're not really exactly dealing with a's anymore. You can't just write like 1 over root 2 root a times 8x because, we never said there was an a anywhere. We want only x's in our answer. So, well, that's not to worry about because we know what a is in terms of x right here. So all we do is plug in. So you plug in right here, 4x squared plus 7 instead of a. Now this plugging in step is exactly this step where you evaluate f prime at g, right? Because we isolated f. Now in this case, our f, our outer function, so to speak, was the square root. So at first, we just had like a square root. I mean, this could have been 1 over 2 root something, right? I mean, that's the derivative of a square root. So you took f prime, but you didn't just take f prime, you evaluated it at g. So g was the inner one, right? So the inner one was this case was, yeah, 4x squared plus 7. So we did exactly the same thing as this writing notation of the chain rule. But at least in my opinion, I think it looks a lot more natural as to, like why we're doing it. I mean, I don't know. In general, Leibniz notation just makes things more explicit. But after you have these two individual derivatives, you can just multiply them. So this over here, right, you have the 8x over here, and then this guy over here. So you go ahead and say 1 over 2 4x squared plus 7 times 8x, and that's basically your answer. And I only see one simplification step here, so you might just say that's 4x. So congratulations, we've now applied chain rule. So now there are certainly a lot of ambiguities with the chain rule because it's certainly not like a well-defined process. So what do I mean by that? So for example, let's just take this example. Well, if you want, sometimes people don't identify the f and g correctly. So then someone might say, well, do I have to identify every single f and g that there is? Do I have to identify every single composition? So for example, maybe someone just skips from like x to, this right away. And then they say, okay, well, if I can't, and then their teacher might mark them wrong or something, if they can't do this sort of derivative in their head. So then this student might ask, well, what's stopping this guy? This guy jumped from here to here, and he jumped from x all the way to 4x squared plus 7. So how can people make that jump? How can people make this jump but not this one? So the real answer, it really comes down to like what you can do with like your stuff outside of your chain rule. Like you try to do as much as you can without the chain rule because it just gets like computationally inefficient. And then afterward, whatever you can't do, you just leave to the chain rule because the chain rule can, in principle, supersede every other rule that you've learned. So, for example, you have x, and then you could, in principle, do something like this, where every single little thing you do to x, you record as another function. So here, we said, okay, apply x squared to x, right? And then multiply by 4. So multiply by 4, and then add 7, and then square root. So we did all of that, right? And we can, if we wanted to, apply the chain rule to each of these individual layers. So we can say, that guy over here over d this guy his neighbor, and then multiply by, and then the pattern continues. So now derivative of this guy with respect to him. And then we continue along the chain of functions like that. And, we can, in fact, get the same answer. Now, this right here, right, we apply exactly the same logic. So we just treat this whole thing as though it was like, as though it was another variable, and then you put it in here. So what we say is, like, you say u equals 4x squared plus 7. And then now you write the whole thing in terms of u, so you get d root u over du. Now, personally, I don't like to introduce new variables. So once you get more experience with it, you might just get in the habit of automatically replacing this guy in here, right? So you search for all occurrences of this function inside this function, and then you just differentiate accordingly. But we might not be as experienced yet, and that's okay. So we would get like 1 over 2 root u, right? So remember, we have u in terms of x, but it's still just u. You can't write x yet, right? Because we've introduced u as a sort of auxiliary variable to keep things straight in our heads, right? So 2 root u. So this is really 4x squared plus 7. And then multiply by, okay, well, this 4x squared, so this is really a something times plus 7, right? So something times 7, if you differentiate with respect to that, you're just going to get 1, right? We can apply the same thing where you assign this to u, so this whole thing becomes du plus 7 du, and then that becomes 1. And then we continue over here, so you've got 4x squared with respect to x squared. So what that's going to mean is, I'll just sort of, so you replace x squared with something, I don't know, let's call it a smiley face this time. So d4 smiley face over d smiley face, so that's just going to be 4, right? And of course, in this case, we're just going to have a 4. If we had 4 and then something in terms of smiley face, then, that would be a different story. We would have to substitute. But in this case, no. So just 4. And then dx squared over dx, well, now you have a 2x right there. So, all said and done, this is going to simplify to exactly the same thing we got earlier, which is 4x over root 4x squared plus 7. Should be the same as what we got before. Yep. So, yeah, in principle, you could use chain rule to do every single problem, but, it depends on how comfortable you are with it. Ideally, you'd want to get to the point where, maybe you have to do this with chain rule, but then this part you can just sort of skip, right? Because what we did here is we went backward every single link like this. We had a derivative for every single arrow that I drew right there. But that might be inefficient. So what you might want to do is just have a single chain rule just for this part. And then afterward, all this you might want to do with a combination of other rules that you've learned. So, basically just use your discretion and try to skip as many steps as you can without making errors or something like that. So that'll be it for this video. This is one of the more important topics. So if there's anything that I should update either in this video or in any other videos, feel free to let me know in the comments or my Discord, which will be in the description. And I will see you guys in the next one.